Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the Editorial Director for Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Pivotal for sponsoring today's event. Pivotal is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Tableau, Microsoft, Hortonworks, Oracle, IBM, and Teradata, to name just a few. By the way, past webinars are available on demand at datasciencecentral.com. If you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled Planes, Trains, and Automobiles, a Data Scientist's Guide to Modeling Engine Degradation. And before we begin, I'd like to briefly review the format of today's webinar. Today's presentation will be an hour long. We have two panelists that I'll introduce in just a minute. There'll be a 10-15 minute Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. So I'm very pleased to introduce today's speakers, Sarah Erny and April Song of Pivotal. So Sarah Erny is Principal Data Scientist at Pivotal, leading the San Francisco practice. She executes projects with customers from pharmaceutical companies and healthcare providers to financial institutions. Before Pivotal, Sarah obtained her PhD from Stanford University in biomedical informatics, performing research at the interface of biomedicine and machine learning. She also co-founded a company offering expert services in informatics to both academia and industry. April Song is currently a data scientist with Pivotal Labs in Santa Monica. Her experience ranges from building predictive models to developing applications as part of a cross-functional team. She's recently worked on a variety of IoT use cases, analyzing time series of smart meters, identifying anomalies in propulsion systems, and inventory optimization in oil and gas equipment parts. Her previous projects include clickstream analysis, a music recommender, and topic modeling. She has interest in all things connected and can speak 3 languages and holds a BS in applied mathematics and a minor in industrial engineering and operations research from UC Berkeley. So thanks for being with us today, Sarah and April. We're looking forward to your presentation. With the growth of connected things, industries are presented with huge opportunities to leverage sensor data to improve their operations, products, and services. With the proliferation of these devices, competitive advantage will develop from appropriate leveraging of this deluge of data. From connected appliances to jet engines, industries are already undergoing massive transformations, and critical to success is the ability not only to collect data from sensors, but to also leverage big data technology and data science expertise to extract actionable insight from the data. It's critical to be able to model degradation of a machine to prevent catastrophic events and adjust maintenance scheduling. This is true in industries including oil and gas, transportation, and even consumer products. In this latest Data Science Central webinar, the Pivotal Data Science team will present a data-driven approach to detecting and tracking jet engine degradation using simulated sensor data. In particular, we'll focus on data integration and cleansing, transformation of time series data into sensor meaningful features for modeling, and algorithms used to build models to identify engine degradation patterns. So April, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Okay, thanks, Bill. Hi, everyone. Thanks for joining. Today, Sarah and I will be focusing on a data science perspective of the Internet of Things, and we'll be going through some specific use cases on modeling. So we'll be talking about jet engines, but IoT is prevalent in all industries. Big data is affecting the way that industries are operating. And with new emerging technology, we're able to collect and digitize petabytes of data, especially more traditional data sources, like medical images. And the plane industry is a field rich with this sort of data. So in our everyday lives, lots of devices are connected. In SF, you can even go see what a connected home looks like. With all the data that's being collected from these connected devices, we want to be able to, make our life easier. When we are running low on milk, can our refrigerator send a text message to our phone, alerting us that, we need to go buy some more milk? And these are questions we're not only asking in our everyday lives, but companies are also asking what can they do with their data to, predict, what can a utility company do to predict if a tree has fallen and identify where it has fallen on a line before residents start to complain. And not just everyday events, but data is also very important to kind of help avoid catastrophic events such as plane accidents. And for this reason, the aerospace industry is an industry that's really embracing IoT. Today, engines are being fitted with more and more sensors. Planes have no less than 250 sensors. And that's just the engine alone. Networks in which data is being transferred has also improved a lot. Traditionally, planes would collect data through their black boxes, and those boxes would have to be manually transferred off the plane, and then the data from that there's a whole other process in loading that data. But now, with improving technology, we're able to kind of stream all that data in real time. And because of this, real-time analytics is also helping improve the efficiency and performance of planes. This is the Pratt & Whitney's geared turbo engine fan. There's 5,000 sensors, and it's capable of collecting up to 10 gigabytes of data per second. So you can imagine a flight from Los Angeles to Tokyo. A 12-hour flight would easily collect over 500 terabytes of data. So why is this a data science problem? Well, how do we take a signal like this and turn it into a data-driven app like that? We do this by being able to take that data, raw data, and recognize patterns from it and use that to kind of determine what actions we can take. The signal might be telling us that there's something wrong in the plane. It could be telling us that maybe a patient is having a heart attack. Or it could even tell us, there's a broken, like a leakage or something in a house. So how can we use data science to solve jet engine challenges? With so much data being collected, there's so many use cases we can focus on. We can predict the thrust demands of an engine that can ultimately reduce fuel consumption and save thousands of dollars. We can monitor the engine health and degradation, which can help with reducing maintenance costs and increasing the performance and efficiency and lifetime of an engine. And last but not least, we can also detect faults and anomalies during the flight. Being able to do this in real time during a flight can help with the prevention of equipment failures or even fatal accidents. So today, Sarah and I will be covering what the data set we used and also the technologies we used to complete the project and focus a little bit on the models and how to build them large scale. So the propulsion dataset comes from the CMAPS, which is a MADlib program that simulates a commercial turbofan engine. It's basically a point-and-click GUI, and you can simulate flights and engine degradation. You can also introduce faults to an engine and see how that affects different parameters of the engine over time. Here's a quick overview of the flights in this data set. I had basically 35 engines, and flights were simulated. Just under 7,000 flights were simulated from those 35 engines. And of those engines, we had a few that had faults introduced to them. And the length of the flights ranged from 74 to 85 minutes. Here are 30 parameters that were collected from the simulation. The parameters were recorded every second during the flight, but you can imagine that in a real flight, there would be thousands of parameters or thousands of sensors collecting data at sub-second sampling rates. I've seen sensors collecting data anywhere from 150 milliseconds to a second. And because of this, we really need to think about what technology is required to process all of this data. So I'll quickly go over what technologies we used here. And to be able to process big data, you need an environment that can be flexible, scalable, and enable you to access and analyze the data. You don't know what kind of data you'll be working with. There's a lot of variety in data. It could be structured or unstructured. You might need to use HDFS, or you might need to use an MPP architecture. You'll also be dealing with petabytes of data, and because of this, it's very important to have a distributed computation framework. And since data science is an evolving field, there's lots of open source projects, and you don't want to keep reinventing the wheel. So we need to be able to leverage these open source packages from Python and R and be able to use it in our framework. And the data should be accessible to tools that you're already familiar with, like Tableau and Spotfire. So analytics with Pivotal. The Pivotal stack has really allowed us to do all the 4 things I mentioned in the slide before. You can, do all the modeling in database and save lots of time and memory. So here's an overview of the Pivotal MPP database. It's a distributed version of Postgres. It forked off of Postgres 8.2. And it basically lets you take a large table, break it up into smaller tables where you can run subtasks to solve one larger problem. So for example, say you have an arbitrary number of cards spread out in your database, and you want to know how many queens are in your deck. You can ask each individual node to count the number of queens, and then take the sum of that, and you have your answer. So Greenplum database is very useful for data science. Like I said, because it forked off of Postgres 8.2, you're able to leverage all of the Postgres functionalities that come with it, like window functions, which allow you to do certain calculations or aggregations within windows of time. You can also leverage the analytics extensions, just like the MADlib library, and also use the procedural languages to leverage R and Python in your analysis. As I mentioned, MADlib is an in-database machine learning library that works with Postgres and Greenplum. You can basically run a bunch of different models. There's everything from regressions to decision trees to clustering algorithms available. And you're basically just calling it from the SQL interface. It's an Apache Foundation project now, and you can see more about it on the website. So another important thing that Greenplum allows you to do is handle embarrassingly parallel tasks using the procedural language. So basically, each node has an interpreter or VM of the language you want to use, say Python or R, Perl, Java, or C. And you can write Python codes within the SQL. And this is particularly useful when you're trying to do a task in parallel. So say I wanted to build a customer churn model for each state, and there's 50 states. I can write a function in PL Python to run these models in parallel. In this case, I might want to run a model for every engine I have in my fleet of engines. Again, I can leverage PL Python or PL R to easily do that. Here's an example of what a PL Python function looks like. You have the create function syntax from SQL, and you have the dollar signs that are the wrappers, and in between the dollar signs, you have your normal Python. So back to this data set. What does a typical flight look like? Here's a plot of 3 flights, and you see that it consists of different ranges of cruisings and descents, climbs. There's a takeoff and landing. And you see during the middle of the flight, there's a cruise at about 35,000 feet for about 21 minutes. And this is the point where the simulation program calculates a snapshot of the engine health based on the values of the parameters during this period. Here's what some of the parameters look like. We have 3 different pressure parameters here, and you see that they tend to kind of correspond to different phases of the flight. And you see that these parameters look like they're positively correlated, but depending on what part of the flight they're in, the correlation might change directions as well. So here's a plot of some of the engines that did not have any faults introduced to them. As I mentioned before, on the y-axis, we have the engine health score, and this is just a value calculated by the simulation program. It's a snapshot of how well the engine is doing in terms of health. And on the x-axis, we have the the nth flight from that engine. And you see here over time that the engine health is degrading exponentially. And we do see some sort of patterns in some of these, in the ways that the engines degrade. Here are some trends that you can see in that previous slide. And it looks like there's at least 4 different ways that an engine degrade. And depending on the way an engine degrading, we might want to use this information to help allocate when and where to use our particular engine or plane that the engine is in. So this is a great opportunity to cluster these engines by the way that they're degrading. Here's what some of the faulty engines look like over time. You see that, again, the health is degrading over time, but when a fault is introduced at the red dot, there's a significant drop in the health. And then it continues on to the degradation pattern. And you see that just because a fault was introduced into the engine doesn't necessarily mean that the planes will quickly degrade any quicker than a healthy engine or an engine with no known faults. So what happens when there is a fault in one of the flights? Well, for the most part, it's really hard to notice the effects of a fault. As you see here in this picture on the left, you can't really tell from the overall time series, but once you zoom in, you start to see a little dip, but it's not always noticeable. On the x-axis we have time, and on the y-axis we have the parameter value, the engine pressure ratio. So again, it's very difficult to kind of spot when a fault has occurred in the raw time series itself. So most of the modeling approaches require us to extract features, and dealing with a bunch of time series, how do we transform the time series into some variables or features that we can then input into a model? So here in this project, we represented the time series by kind of chunking it up into windows. Each flight, like you saw earlier, has different climbs and descents and cruising phases. So for each of these phases, we first identified each phase and then calculated different statistics during those windows, such as the mean, the min, the max, standard deviation, so on and so forth for the time series in that given window. And then we also took the summary statistics on the rate of the change of the parameters within those given windows. Another thing we looked at was how correlated are two sensors, and do these correlations between sensors differ flight to flight? We looked at the correlations in two ways. The first was looking at the correlations on the overall data set and observing trends, and then the second was looking at correlations for each flight and observing the trends there. So here's a chart of distribution of the correlations between sensor pairs. There were a total of 435 distinct unique parameter pairs. And we see that 168 pairs of these are strongly positively correlated, and about 230 pairs are weakly correlated. Here's a slide on just the top negatively and positively correlated parameters. I'll kind of skip over this for now. Here's a plot of the top negatively correlated parameters, and you do see that they're almost perfectly negatively correlated. And here's a plot of the positively correlated sensors. Now, if you take a look at the correlations and the altitude, you see that there is a change in correlations between parameters during the, depending on the phase of the flight. And these colors, orange, green, and blue, represent the flight IDs. So you're looking at three flights plotted here. And you see that at takeoff, the correlation's pretty, there's like little correlation, it's hard to tell. And the correlation values just change over the course of the flight. So here the flight is ascending or climbing. Here the flight is climbing again, but it's climbing at a quicker rate. And you see that there's been a change in the correlation between altitude and P2, which is a pressure parameter. And here again, you see that the plane is climbing, but at a much slower rate, and you see another change in the slope of the correlation between the two parameters. And again, here at the end when it's in cruise. So it's very important to kind of look at what these sensors are doing depending on the flight or depending on what the plane is doing. Is it in cruise? Is it in takeoff? Is it landing? So now I'll talk about clustering these flights and getting some insights on how the engine is degrading over time. So the algorithm we use is k-means clustering here, and the objective was to group flights based on their parameter time series. First step was, again, extracting the summary statistics and turning those into features for the time series for all the different phases. And then there was some feature selection. I won't go into details about that today, but after the feature selection, we used MADlib's k-mean algorithm to run the modeling. And this is all done in database. And you repeat this model for the 29 other parameters. So at the end, you end up with 30 different k-means clustering models, one model for each unique sensor parameter. Here are the results. You see here that the time series for the Smfan parameter has some interesting results. It looks like when a flight enters the fourth cluster, it could be indicative of the engine's end of life. On the y-axis here, you have the number of flights, or the nth flight, 0 to 300. And on the, sorry, that was the x-axis, and on the y-axis, you have the different cluster numbers for the different engines. And it seems like, you know, for this particular example, flights that ended up in cluster 4 indicated that the engine was nearing end of life. So this could be very useful in terms of scheduling maintenance, scheduling maintenance or repairs, or even retiring a fleet of retiring an engine. And now I'll pass it to Sarah, who will go over some classification-based similarity metrics.
Great, thanks, April. So we're going to cover next this concept of taking a classification-based approach to being able to compare differences that might be occurring over flights for a particular engine. So what we did for this particular project, and this part of it in particular, is to go through and look at the various features that April already described for a given phase of a flight. So the goal really is to be able to look at any engine and compare its behavior from one flight to the next by using a classifier that's going to be able to build or predict whether or not a sample from a small time window came from one flight or another. At a high level, if we think about what it is that we're going after, let's imagine we have 3 classes here represented on the right, and those will ultimately be small windows of time that we've selected from a period, for example, takeoff or cruising. And those are the types of features that April has already described. So we have represented here on the right are these 3 classes, which could be a collection of windows. It could ultimately be any sort of data set that you're working with, where you're trying to establish a distance metric between all pairs. Ultimately, we can see on the left-hand side, Class 1 and Class 2 could be visually represented as these dots where their size and color differ, for example. And if we take a sample of each one of those classes and build a classifier, we'll be able to differentiate, likely based on the features available, for example, color and size, whether or not any new example comes from Class 1 or 2. Using this, we'd be able to have a high model accuracy for being able to classify or differentiate between Class 1 and Class 2. Now, if we look at Class 2 and Class 3 and we build another classifier here, again, sampling from each, building that classifier, and then what we can do is take the remaining held out set and ask the question, how well can we differentiate those 2 classes? When we have low model accuracy, that's indicating that we are unable to differentiate between those 2, and therefore are highly similar given the features that we've created. So really what this allows us to do is take a sort of supervised approach for being able to select a set of features that allow us to differentiate between the attributes of these 2 classes. Now, the way we're going to do this with the actual flight-based information that we're working with is we're going to look at flights pre-takeoff, and we're going to take a set of non-overlapping windows of 5 seconds. From these, we're going to extract the types of features that April has already described. For example, the correlation across the various sensors, means, standard deviation. And for each one of these windows, we can now treat them as a training or a test example from a given flight. So if we trace one engine, we're able to now, if we look at this next slide, split it into the multiple classes, and for a given engine, Flight 1 versus Flight 2, we can build a classifier for those individual 5-second windows that we separated out as a training set, and then ask the question, what is our accuracy on the held out set? And that accuracy can be used as a proxy for similarity. Again, high accuracy means we are able to differentiate, and therefore there is some difference between Flight 1 and Flight 2 in terms of the engine's behavior or attributes that we selected. If they are very similar to each other, we would be unable to build a very good classifier, and that would mean that these two engines look the same. What we ended up doing for the data set that April has presented so far is we were able to build these classifiers for any given engine across all of its flights. Let's take an example of a flight that has flown 3. We would build a classifier between flight 1 and 2, flight 1 and 3, and flight 2 and 3. Again, these non-overlapping 5-second windows from pre-takeoff are used as both the training and held-out test set. Now, for the environment that we had set up, we had to run close to 750,000 models, and it took about 11 minutes for us to run that in a 128-segment cluster. The approach we took was the one that April described, again, using the database, and specifically using the PLR functionality. So we were able to use models in R, or it could have been Python as well. We have the ability to use Perl, Java, C, to be able to run these types of models in parallel in the database. So they're all run at the same time, allowing the data to not move out of the database and simultaneously taking advantage of the parallelism offered by the database. What we were expecting to see out of this is, of course, adjacent flights for a given engine should look pretty similar to each other, meaning that they would have low accuracy. We're unable to distinguish the windows from one particular flight to the subsequent flight. However, we would expect as an engine begins to degrade, we would be able to differentiate, as the particular samples of windows would look very different from each other. What this would look like is if we plot model accuracy over time, as time here represented by the flight particular instance, we'd be able to grab, for example, this instance in the middle, represented by that reference flight dot, and for all flight numbers before and after that are immediately adjacent, we would expect extremely low model accuracy, meaning, again, our classifier is unable to differentiate a 5-second window coming from this flight versus a flight just prior or just following this particular reference flight. Now, the ones far away should be easy to differentiate because there should have been some change that occurred in the engine, and now we'd be able to recognize things about this current reference flight that are different from the ones that were long ago or in the distant future. When we did this on the actual data, what resulted, let's take this particular example for engine 1, we built models where, again, on the y-axis here, we're looking at the accuracy score for the classifier, here for reference flight 8, as compared to all of its nearby flights and also the ones in the sort of distant future. What we can see on the x-axis, again, are the flights. Flight 2, meaning the one that's being used as a comparison point to the reference flight 8. We can see that the nearby ones, although there's difference, of course, in the accuracy, there's lower accuracy overall, and the ones very late on in the range of 200 plus flight number are highly accurate, meaning very different. So we're able to easily differentiate anything coming from flight 8 from, for example, flight 200. Now, when we also plot engine health, what we can see is that there is some sort of a correlation between the accuracy and the health, indicating that potentially some pieces of the unhealthy attributes of the engine are being captured as well, allowing us to understand engine degradation a bit. Now let's see what happens as we begin to move forward, and let's pick another particular reference flight. So here, let's take flight number 47. What we see is a change in the shape. We're, again, looking at flight number 47. Those that are nearby have a low model accuracy, meaning we can't differentiate them well. And again, the ones in the future have high model accuracy, meaning they look quite different. Now, another attribute that we might be able to look at is understand what the average score or accuracy is when we compare flight 47 to all flights that came before. And we can see that there is a low accuracy, meaning this particular flight looks very similar to the flights that came before. Of course, if we look at everything after, there's a higher accuracy, meaning it looks very different from everything in the future. So as we click through these reference flights, going further along in the engine life cycle, we can see that we begin to also now be able to differentiate, for example, flight number 115 from much earlier flights. indicating that there likely has been some change in the engine itself that is captured now by this classification-based technique. Finally, when we get to the very end of the actual simulation for this particular engine number 1, we can see that for flight 255, while there is some difference between flight 255 and the handful that follow, there is, again, very high model accuracy for those that came prior, meaning that there has been a significant shift. What we can see is even the very nearby ones have changed. Interestingly, in terms of engine degradation, we're also seeing that there has been a significant change in engine degradation here as well. Now, if we take this data and we plot it, see here as a visual on the heat map where the color light green indicates very dissimilar, meaning extremely high model accuracy, so our classifier is able to distinguish, and dark green meaning low accuracy, meaning unable to distinguish. We can see that early on the Y and the X-axis, we have flight number. So on the bottom left-hand corner, we have early flights that look quite similar to all other early flights. Of course, this is a symmetric matrix here for the most part. So what we're going to end up seeing is as the engine begins to perform more and more flights, it becomes more and more dissimilar, of course, from the nearby and far away flights as the engine degrades, and we're unable to, and we are now able to distinguish the different windows from each other. Now, what's interesting is if we look at this in particular for engine 1, we can see that up until flight 50, we really see a lot of similarity as the engine is in its early stages and quite healthy, but this changes very rapidly over time. Now, while this is quite useful for us to be able to understand at a high level what's going on, we'd like to understand how we would observe significant changes in degradation or even something like a fault. And one attempt that we had for going after this is if we look at the model accuracy that we observed over time. Here on the y-axis, again, we have model accuracy, and on the x-axis, we have the reference flight as compared to all other flights. We can understand that if we're looking at sort of the mid-range of a healthy engine, yes, it would look dissimilar from flights that are very early coming before or have occurred later, but I'd like to understand kind of what's happening to the engine to be able to understand what happened prior to it, really. So we can see that there was quite a bit of a difference in the shape, which we're kind of plotting here as a line. And what we decided to do was use some summary statistics to understand what had happened to flights preceding this particular flight by looking at mean and median accuracies across all of those pairwise classifiers that were created. Now, what happens is that ultimately we'd be able to potentially detect an anomaly or something extreme that has happened where there's a significant shift from one flight to the next in terms of model accuracies of the preceding flights. So let's plot a bit what this would look like. So if we're looking at engine health using the blue line here. And again, this is from the simulated data, so this is something that was computed from cruising for a particular engine. We can see this blue line on the left. It starts out fully healthy, and over time it degrades. Now, in addition, what we've done is plotted the median accuracy score for the particular flight number for all flights that came prior in green. So we can see that in the beginning, we're unable to really differentiate very well from everything that came before. And over time, if you look at the green line, it begins to increase, meaning there has been some shift, which seems to actually sort of anti-correlate with what's occurring in terms of the engine health score. Just for completeness, we've also plotted in orange the accuracy for what comes after, which might be interesting to use at some other point to understand kind of the way you would look at degradation in a post-mortem situation. Now, one interesting thing is if we look for abrupt changes in that engine health, would we also be able to see abrupt changes in the median accuracy for our distance metric for all of the flights that came before? To answer this question, what we did was look at many of our flights and compute the same pairwise distance metric, and again, compute the median for any given reference flight for all of the flights that came prior to it for that engine. So here we've plotted in the various colors all of the different engines. On the top, we have the median accuracy score on the x-axis for a given flight number for that engine for all of the accuracies that came across. And on the bottom, what we've plotted as well is the engine health score. Again, on the y-axis, the actual health, and on the x-axis for that engine at that flight, what the score was. Now, if we look and call out one particular engine, here this is an example of an engine that stays pretty flat. So this is an engine that really is not degrading over time, so we assume the efficiency stays high. And we can see that although there is a bit of a change in the actual, on the top plot, model accuracy as we proceed, it does look different if we look at this one that degrades rapidly in terms of shape from a different type of engine profile as the ones that April described earlier. So here in purple and blue, we're showing two engines that actually degrade much faster than the prior one. And you can see that the shape is significantly shifted to the left for those top plots for median accuracy, indicating that that accuracy score really in some ways is capturing this concept of a more rapidly degrading engine. The other thing that's quite promising about that is we can see, for example, the purple engine, which degrades faster on health score, is showing a shift as well at the top for that median accuracy to the left compared to the blue. So we're able to understand degradation by looking at these patterns. Can we try and understand what's happening in terms of engine fault as well? So here what we've done is taken engine 32, and we've plotted what is happening again in blue in terms of engine health. And we've also indicated when the fault itself occurs with that arrow. So you can see that it happens sometime around flight 10. We've also plotted again that median accuracy for, in green, all of the distance metrics for that particular flight prior to it, and then in orange, after. Again, plotting after is something quite arbitrary. When we're trying to understand what has happened in terms of a fault, we'd want to know at that time, could we predict a fault may occur, but it might also be interesting if there isn't good understanding or detection of a fault, whether or not this would have been an approach for going after it. Now, we can see that although there is, again, a shift from the green in terms of the accuracy for all flights prior, we can see the fault itself doesn't seem to be something that's so readily recognizable in this particular instance. As a reminder, April showed us several different types of faults. So if we look at another fault, an HPT fault in particular, we can see here indicated on the left, again, the health score in blue, there's a big drop. And we're also seeing in green the median accuracy shift for all flights that came before. So we can see that at the time of the fault, there was a sudden change in terms of what we're seeing for median accuracy. On the right-hand side, we've decided to kind of plot that out. So we have flight number 28 on the left and flight number 29 on the right. What happens is prior to the fault, you can see that the difference in terms of median accuracy is shifted. So the green dots are lower on the y-axis, meaning that they look quite similar to the given flight. And then post-fault, we can see that they're shifted up, meaning that the similarity now is not present. So we're able to differentiate post-fault that something has occurred. And the engine looks very different in flight 29 from 28, and certainly from 27, as compared to the prior 28 and 27. What this might allow us to do, for example, in this instance, would be to detect that a fault has occurred, if there's no other way to detect that. Here we have another example of an LPC fault. Again, we're seeing on the left-hand side that there is a slight shift here in engine health. But what's significant is that although the engine health itself isn't showing a big change, the model accuracy is showing a big change. So again, we're seeing a big shift in similarity. So the engine looks very dissimilar from prior flights now as compared to pre-fault. Ultimately, what we wanted to ask, though, in terms of median accuracy and engine health, we'd like to know whether or not what we're detecting really at all times has something to do with sort of just an engine over time getting older, and therefore it's the number of flights that's affecting what is happening as compared to an actual engine health change. So what we decided to do for the various faults was look at the actual engine health over time and compare on the y-axis, and then on the x-axis and the y-axis look at the accuracy score. And what we can see is that in color here we're showing flight number. There actually is a stronger correlation with engine health and accuracy than there is with the actual number of flights, indicating that it doesn't actually have much to do with the change in sort of number of flights that's influencing it, but it's actually the change in engine health that we're observing. Now, ultimately, that's something that's interesting for us to look at across different types of faults. So here we're showing the 5 types of faults that were modeled. So what's interesting here, again, this is much zoomed out, so it's still color is representing flight number, and the x-axis is the engine health, y-axis is the median accuracy. We're seeing that in general there is a correlation, but we can also see that the relationship between them is quite different, and this may be a way for us to actually understand when a fault occurs or not. But it is, again, mostly engine health related, although, again, LPC, for example, does seem to show a very different relationship from HPT faults. So this type of work really allows us to understand that the classification-based distance metric is allowing us to observe changes in engine health, may be very useful for detecting faults, and ultimately could allow us to do some sort of root cause analysis as well in terms of looking at the features that allow us to differentiate an engine post and pre-fault from each other. With that, I'll pass it back to April.
Thanks, Sarah. So here's a quick recap of what we covered and what's next. We learned that, with new technology, we're now able to more efficiently go through lots of data, huge volumes of data, especially sensor data. And, now I'd recommend going into some more advanced time series modeling and, interpolating the missing data. And then we also talked about experimenting with different models to predict the engine decay and faults. We learned that unsupervised techniques for clustering and using distance metrics help us discover signals of decay in our data. You can also try a supervised approach to detect known faults. I didn't try that with this particular data set because the data was entirely simulated, so in a way it would be kind of reverse engineering that model. But with a real data set, this would be another interesting use case. So with that, we have lots of things in our everyday lives connected, and ultimately, with all that data and all that connection, we want to build a digital brain. And this can help transform many industries, from security to personalized medicine to the auto industry. And we see that it's even changing the aerospace industry with the way that things are speeding up in terms of loading the data from the plane and off. Okay, and now I'll pass it back to Bill.
Okay, well, Sarah, April, thanks for that very interesting presentation. We'll get started with today's Q&A session, and I want to thank the audience for their participation. We've had a lot of questions that have come in during the presentation, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Sarah and April, in case you'd like to contact them following today's webinar. So let's get started. You demonstrated a great many different types of analysis that you applied to this simulated engine data. Were there models that you would have liked to have built that would have been interesting that you just didn't get around to? Where does this go in terms of modeling?
Yeah, so because I was working with a simulated data set, all these flights had the same behavior, same patterns. But in a real data set, you'll see that planes are, going up at different rates, or there's a lot more going on in a flight plan. So another model you can build is a clustering model using the time series. You can use fast Fourier transform to transform the time series into periodograms and cluster those. And ultimately, you can kind of get groups of similar flight plans. So you might get one grouping where two flights went up in the air once and then back down, and then you might get another cluster group of flights where you see the plane going up and down multiple times.
Right. And as a matter of fact, the audience would like to know if they can share in this data set. Is it possible for the public to have access to this data set to work with?
Yeah, it's available. It's available off of the NASA website. I think if you just Google propulsion engine data NASA, you might be able to see a link. If not, I can add it to the slide here before you upload the slides.
Okay. Well, thank you. This is simulated data, and you might tell us a little bit about in what way it's simulated, because I've had a bunch of questions that relate to, I think, more real-world circumstances. For example, if the data had been from different jet engine manufacturers or different sensors, you would have presumably had to do some additional steps to normalize. Can you comment on the difference between the simulation and what a real-world circumstance might be?
Yes, absolutely. This data set was simulated the way April already described using that particular program, which is actually frequently used in this space. We also have worked with real jet engine data, and there are differences even within one particular engine from one to the next. So luckily, our environment allows us to do these types of normalizations quite easily, and in our other work, that is exactly what was done. So it's easy to get summary statistics across a window of time for a given engine using SQL functionality. And it does allow you to bring those data sets together by looking at things like changes over time, which is precisely the type of thing that we're trying to look for. But yeah, that is absolutely accurately stated. Even if you're taking off from one airport versus another, differences in altitude there, here in a simulated data set, we can say we're starting at 0. The concept of 0, of course, is different between San Francisco and LAX airport, for example. So SQL functionality is critical in those instances.
Oh, yeah, interesting. And this may also be an issue of simulated data versus real-world data, but IoT data is notoriously dirty. Was your simulation data already complete? Was there missing data? Did you have to deal with interpolation of missing data or replacement of missing data?
Yeah, so the data was somewhat clean, except the sampling rates weren't consistent across all the flights, so there was a little bit of interpolation done there. I did inverse distance weighting for that, which basically takes into account the neighboring time samples to determine the missing values.
Okay, and do I remember correctly from the presentation that your time window was 5 seconds, and did you average across that 5 seconds, or how did you treat the grouping within that 5-second window?
So for the particular simulated data that was described here, we did use the 5-second window. In other data sets that we've worked with, so April already described there were differences in sampling rates, for example, that had to be accounted for, so she uses inverse distance weighing. We experimented with different sized windows to see what the outcomes would be. And again, having the opportunity to run these models really quickly allows us to do just that. So we're able to change a different window. In terms of the types of features, yeah, absolutely. So we toyed with a few different features, but for a given window, you might look at the average pressure, the standard deviation of the pressure, the correlation of a pressure, and maybe another sensor. So these changes are things that allow us to understand from a data-driven perspective what is happening to the sensors, and over time windows engineer different features that now let us say, okay, what does the data tell us is significant to allowing us to understand the difference between, for example, Flight 1 and Flight 2, or in the clustering instance, it allows us to see differences across the different engines.
Right, thank you. Thank you for that answer. One of the things that caught the audience's attention, and Sarah, I think it might have been you who said there were, I think, over 45,000 different models that you had to run, if I've got that number correctly. Was there some automation involved, or did that all get hand-coded?
Absolutely. So the way that we run these types of models, you can imagine creating a function, Python or R, I can't even remember, because for us it's quite simple. The way April described, you drop in the particular code that you would use. For example, if you're using a random forest or a regularized regression, that takes in the features, runs it, and then returns back whatever it is. We were using the different accuracies as returns on the test set that was brought in. So what it allows us to do is create a function the same way you could have an average or a standard deviation. Instead, it's a more complex function that runs R code or Python code or uses any of the libraries that's registered to the database. And it allows us to select from a table and run that particular function and group it by engine number or pairs of flights. And that allows us to run these all in parallel. So it's absolutely not hand-coded for every single one of these. It's done by using joins and functions.
Okay. Yeah, well, 45,000 would be a lot. Here's a question that's a little more technical in nature. So why looking at correlation between sensors helps us to detect plane health or degradation? Is it a prior assumption just for airplanes that the sensor's correlation will change when the plane degrades?
Yeah, absolutely. So I think I mentioned this earlier. The concept of using correlations, we on the data science team are non-experts in aviation, and what we are learning is how to use the data to allow it to speak for itself. So it's pretty easy to engineer these types of features over a window of time. When you have a lot of samples, you can run correlations between all pairs of those parameters and allow the model to say whether or not that was a significant feature. Of course, when we interact with the domain experts, they're able to tell us some of those things. But if there are changes that are occurring, we'd be able to detect that if something is consistently correlated, the way April described earlier, there were some strongly correlated features, particularly when you looked at a given phase of that engine. So let's say during cruising, maybe pressure and altitude are highly correlated. Maybe if there's a change inside the engine pressure, that would be something you would detect, which would be a change in correlation. And that would be something that the model itself would be able to produce. So what we do is engineer a lot of features and allow essentially the algorithms that are out there for being able to detect this correct subset of features to be able to differentiate, to actually allow the data to determine what is correct and allow us to use creativity and domain expertise to engineer those features.
Terrific. Yep. Let the data tell the story. Earlier in the presentation, you had divided the flight patterns into phases. So the audience asked, how did we determine how many phases on a time series plot? Was this strictly the mechanical issue of takeoff, increase in altitude, cruise, and so forth, or was there a mathematical technique involved?
It was a little bit of both. So for takeoff and landing, you know that the plane is on the ground. So I marked those phases as such. And for climbs, I detected the point in time where the plane's altitude changed from a slope of 0 to a rate of change of 0 to a positive rate of change, meaning the plane is climbing up. And as for the plane descending, you know that at that point the change in altitude should be going down. And for cruise, I found the parts where the altitude remained constant. And to do all these, to find all these phases, I used window functions to detect when the altitude was changing.
Okay, good. Makes perfect sense. Well, Sarah, April, thank you for some great answers to some very good questions. For those of you that asked questions today that weren't answered, we'll be sending those unanswered questions to Sarah and April and the Pivotal team so they can follow up with you following today's webinar. I have just a few quick announcements. Please mark your calendars for April 12th. That's our next Data Science Central webinar. Also, please remember that today's taping will be available for on-demand viewing later today and can be found on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks to Pivotal for their sponsorship and our speakers today, Sarah Ernie and April Song, for their insight in the topic. My name is Bill Voorhees. I'm very pleased to have been your host for today's event, and I look forward to seeing you all again on April 12th. Have a great day.